Humanity is about to graduate from exploring planets to building them. The emerging field of astroengineering gives us the blueprints to transform entire worlds, turning barren landscapes into lush, living habitats. In this journey, you will discover 20 specific concepts that could literally reshape the future of our species in the cosmos. We will uncover how we might give a dead planet a new atmosphere and what happens when we discover life already there. Does our desire to build new Earths come with a price we are prepared to pay? This ambition to build new worlds rests upon a single, monumental discipline. Astroengineering is the ultimate expression of human ingenuity, a field dedicated to the deliberate and large-scale modification of celestial bodies. It is far more than just setting up a base or planting a flag. This is about fundamentally altering a planet's very identity, from the composition of its atmosphere to the flow of its geology, and even the precise path it takes around its star. We are talking about merging the principles of astrophysics, climatology, geology, and biology into one unified practice of planetary-scale construction. The core idea represents a profound shift in our cosmic role. We would move from being mere observers of the universe to becoming active participants in its shaping. This is not a small step, it is a leap into a realm of almost unimaginable power, and with that power comes a responsibility we are only beginning to comprehend. Grasping this foundational concept is essential, as it sets the stage for the incredible and specific ideas we are about to uncover. Carl Sagan once proposed a way to cool the scorching surface of Venus. His was not a blueprint but a question, a spark that ignited a new way of thinking. This intellectual lineage connects the dreamers to the doers. Science fiction authors like Kim Stanley Robinson then took that spark and built entire worlds with words, meticulously chronicling the generational struggle to terraform Mars in his famous trilogy. These stories did more than entertain, they provided a narrative framework for a scientific possibility, making the immense challenges of planetary engineering feel tangible and human. By the closing decades of the 20th century, these thought experiments began to seep into the halls of academia and government agencies. NASA started funding serious studies into planetary atmospheres and climate modeling, transforming what was once pure speculation into a field of legitimate scientific inquiry. The dream was slowly being fortified with data, equations, and computer simulations. This entire journey, from the pages of a novel to the research proposals of a space agency, demonstrates a remarkable acceleration of human ambition. We are now standing on the shoulders of those early visionaries, ready to explore the tangible concepts that could turn their grandest dreams into our future reality. The first concept brings our ambitions into sharp focus with orbital mirrors and sunshades. Think of these not as simple pieces of glass, but as planetary-scale thermostats. For a cold world like Mars, we could position vast, feather-light mirrors in space to act as a second sun. They would concentrate sunlight onto the planet's frozen poles, which are not just made of water ice but are capped with vast reserves of solid carbon dioxide, what we call dry ice. Heating these caps would be like turning a key in a lock. The frozen carbon dioxide would sublimate, transforming directly from a solid into a gas, and pour into the thin Martian atmosphere. This deliberate release of a potent greenhouse gas would be the first crucial step in trapping solar energy and warming the entire planet from the ground up. Now consider the opposite problem. Venus is a world choked by its own thick atmosphere, a victim of a runaway greenhouse effect that bakes its surface. For such a world, the solution would be a colossal sunshade, a structure so large it could partially eclipse the sun from the planet's perspective. This would not be a single solid sheet, but likely a cloud of billions of tiny, autonomous reflectors, positioned at a stable point between the planet and its star. By deflecting just a few % of the incoming solar radiation, this orbital shield would, over centuries, allow the planet to radiate its immense heat away into space, slowly and steadily cooling its hellish surface to a more manageable temperature. The engineering behind these ideas pushes the boundaries of what we can build. These mirrors and shades would be constructed not on Earth, but in the zero-gravity environment of space, using nanomaterials thinner than a human hair and lighter than a feather. They would need to be self-repairing and maintained by a fleet of autonomous robots, a silent ballet of machinery operating far from human hands. While the scale is almost beyond comprehension, the principle is one of gentle, persistent influence. It is a method of coaxing a planetary climate toward habitability rather than forcing it, a first, delicate touch in the long process of building a new world. This initial manipulation of sunlight sets the stage for the next, even more direct intervention, one that works from the inside out. The oppressive atmosphere of Venus is not just a barrier, it is a vast, untapped reservoir. Imagine confronting this immense, swirling ocean of poison and seeing not a problem, but a solution waiting to be unlocked. This is the core of our second concept, atmospheric processing platforms. These would not be simple machines, but colossal, automated factories designed to float high in the Venusian sky, suspended in the more temperate upper layers of the atmosphere. Their mission is one of planetary-scale alchemy, to take the very substances that make the planet deadly and transmute them into the building blocks of life. They would target the two primary components of the toxic air, the overwhelming carbon dioxide and the corrosive sulfuric acid clouds, using advanced chemical processes powered by the intense, unfiltered sunlight above the cloud tops. These platforms would work tirelessly. They would pull in the thick atmosphere, break the powerful molecular bonds, and separate the elements. The carbon dioxide would be split, capturing its carbon for industrial uses and releasing its oxygen to slowly build a breathable layer. The sulfuric acid would be similarly dismantled, yielding its hydrogen, which could be used for water production, and its sulfur, another valuable resource. This is a profound reversal of logic. Instead of fighting the environment, these platforms would work with it, using the planet's own overwhelming atmosphere as the raw material for its transformation. It is a slow, patient process, one that would take centuries to complete, but it represents a shift from forcing a world to change to persuading it to become something new. The sheer scale of such an operation forces us to think differently about construction and industry, leading to an even more fundamental question. What if we could grow our tools and habitats rather than build them? Orchestrating a celestial collision sounds like an act of pure destruction, yet it could become our most powerful tool for creation. This third concept, directed asteroid impact, turns the most feared event in our cosmic history into a deliberate act of planetary engineering. The target would be a dry, resource-poor world like Mars. The method involves selecting a small, water-rich asteroid or comet from the outer solar system, a cosmic iceberg holding the very ingredients a barren world lacks. With immense precision, we would nudge this object onto a new trajectory, guiding it on a slow, calculated fall toward the Martian surface. The impact itself would be a controlled cataclysm. The sheer kinetic energy released upon collision would be staggering, translating into an immense pulse of heat that would help warm the planet's frozen crust. But the real gift is the impactor itself. As it vaporizes, it would release its precious cargo, a wealth of volatiles like water ice, ammonia, and methane. These compounds are the fundamental building blocks for an atmosphere and a water cycle. They are the raw materials a planet needs to begin holding onto heat and, eventually, to support the complex chemistry of life. This is not about random bombardment. It is about a single, precisely targeted delivery, introducing the essential elements for a biosphere from an external source. The ethical and practical challenges are profound. The process would require a level of control over celestial mechanics we do not yet possess, ensuring the impact occurs exactly where and when intended to prevent unintended global consequences. It is a reminder that our power to reshape worlds must be matched by an equal measure of wisdom and foresight. After such a dramatic intervention, the planet's surface would be a blank canvas, awaiting the next, more delicate phase of construction. The most powerful tool for transforming a world might not be a machine, but a microbe. We can move beyond engineering the environment from the outside and begin programming life itself to rebuild a planet from the ground up. This is the promise of genetically engineered terraforming organisms. Picture the first mission to Mars not with construction crews, but with canisters filled with a silent, waiting army of custom-designed bacteria, algae, and lichens. These are not ordinary life forms. They are biological machines, their very DNA rewritten to not just survive the harsh Martian soil, but to actively consume its dangers. Their primary food source would be the toxic perchlorates that currently poison the ground, transforming these hazardous chemicals into harmless salts, while, as a byproduct of their metabolism, they gently release oxygen and other gases into the thin, cold air. This is a process measured not in years but in centuries. These pioneer organisms would be the foundation of a new biosphere, working tirelessly across generations. As they spread, they would slowly condition the soil, making it fertile and ready for the next wave of colonists, perhaps hardy genetically modified plants designed to anchor the soil and accelerate the production of a breathable atmosphere. The beauty of this approach is its self-sustaining nature. Once established, these biological engineers would propagate on their own, a living system that expands and works autonomously, using the planet's own resources to fuel its transformation. This gentle, biological coaxing presents a stark contrast to the brute force of asteroid impacts, offering a path to habitability that feels more like a slow, natural awakening. But what happens when the scale of life we introduce grows from the microscopic to the monumental? A planet's magnetic field is its silent, invisible guardian. For a world like Mars, this shield is gone, leaving its surface naked to a constant barrage of radiation from the sun and deep space. This is not merely an inconvenience for future explorers. It is the single greatest barrier to establishing a permanent, thriving civilization there. Without protection, this radiation would slowly degrade any atmosphere we manage to create and pose a severe, long-term health risk to any living thing on the surface. The solution, however, might not involve rebuilding the planet's molten core, but rather giving it a new kind of artificial heart, positioned 1,000,000 miles away in the void of space. The concept involves placing a remarkably powerful magnetic field generator at a precise gravitational balance point between Mars and the Sun. This location, known as a Lagrange point, is a place where the pulls of the two bodies cancel each other out, allowing an object to hold a stable position relative to both. At this strategic outpost, the device would activate, generating a concentrated magnetic field that would inflate like a vast, invisible bubble. This magnetic shield would then act as a planetary-scale umbrella, intercepting the relentless stream of charged particles from the solar wind and gently deflecting them around Mars. The effect would be twofold. First, it would immediately begin protecting the planet's surface from the most harmful radiation, making it safer for human habitation. Second, and just as crucially, it would stop the solar wind from constantly stripping away the upper layers of the Martian atmosphere, a slow leak that has been occurring for billions of years. By halting this erosion, the artificial magnetosphere would allow any new atmosphere we create to remain stable and build up over time, rather than being blown away into space. The energy needed to power such a colossal structure is almost beyond imagination. It would likely require vast arrays of solar panels, stretching for miles in orbit around Mars, or perhaps even compact nuclear fusion reactors, technology we are only beginning to harness. This concept forces us to think on a truly cosmic scale, not just altering a world's surface, but weaving a protective barrier for it in the space it travels through. It redefines what it means to build a habitat, reminding us that a true home needs both a foundation and a roof. With such a shield in place, the surface of Mars would finally be a place where life could take root without being burned away, setting the stage for the next, even more intricate phase of its transformation. Beneath the rust-colored deserts of Mars lies a secret ocean, not of liquid water but of ice. This is the target of our sixth concept, the hunt for subsurface aquifers. These are not mere patches of frost, but colossal reservoirs, frozen relics of a wetter past buried deep underground and locked within vast glaciers. To awaken this sleeping giant, we would deploy networks of robotic drilling platforms, machines capable of boring down through miles of rock and permafrost. Once they reach their target, they would not simply pump water out. Instead, they would use focused geothermal probes, essentially artificial hot springs, to slowly and steadily melt the deep ice in place. This creates a sustainable, underground source of liquid water that can then be carefully brought to the surface. The moment that first flow reaches the open air is the moment Mars truly begins to change. This water would initially collect in prepared basins, forming the first new lakes and small seas the planet has seen in billions of years. Even these modest bodies of water would start to influence the local environment. They would create microclimates, with evaporation leading to cloud formation, and perhaps even the first gentle, localized rain showers. The water itself is more than just a resource for drinking or irrigation. Using solar energy, we could split every molecule, breaking it apart into its core components. The hydrogen becomes a powerful fuel for industry and rockets, while the oxygen is released to slowly, molecule by molecule, thicken the atmosphere and make it breathable. This process of tapping hidden aquifers is the foundational act of creating a hydrosphere. Think of a hydrosphere as the planet's circulatory system. It is the continuous movement of water from the ground to the sky and back again, a cycle that regulates temperature, distributes nutrients, and ultimately makes complex life possible. Establishing this cycle is the critical, non-negotiable first step before any advanced ecosystem can hope to take root and flourish on a world that has been dry for eons. With a functioning water cycle beginning to stir, the stage is set for the next, even more intricate phase of planetary development. The slow biological release of oxygen is a gentle beginning, but some worlds demand a more immediate intervention. We can think beyond coaxing the environment and begin actively weaving a new climate into existence. This leads us to the concept of artificial greenhouse gas production. Imagine vast, automated factories standing on the cold, silent plains of Mars. These are not belching industrial plants of old Earth, but silent, efficient facilities powered by the relentless Martian wind or vast fields of solar panels. Their sole purpose is to manufacture specific, incredibly potent chemical compounds, primarily perfluorocarbons. These are not naturally occurring gases. They are human-designed molecules, engineered to be thousands of times more effective at trapping infrared radiation than carbon dioxide. As these facilities release their synthetic product into the thin atmosphere, they are not just adding gas, they are stitching together a planetary-scale thermal blanket. Each molecule acts like a microscopic trap, catching the sun's warmth that would otherwise bounce back into space and holding it close to the surface. This is a deliberate and controlled acceleration of a planetary warming process. The goal is to raise the global average temperature by dozens of degrees, pushing it past the critical point where water ice can no longer remain frozen. This is the crucial threshold, the moment when the first liquid water could pool and flow on the surface for the first time in billions of years. The beauty of this synthetic approach lies in its precision. Unlike the unpredictable release of a planet's own carbon dioxide reserves, the production of these artificial gases can be dialed up or down with the flip of a switch. If warming proceeds too quickly, we can simply reduce output, giving the planet's evolving systems time to adjust. It offers a level of management that more chaotic methods lack, turning the monumental task of climate control into a process we can carefully meter and monitor. This act of building a climate from scratch forces us to confront a profound responsibility. We are not just altering a landscape, we are becoming the architects of an entire world's weather, its seasons, and its very potential for life. The silent machinery of planetary transformation demands an immense and constant voice of power. Every atmospheric processor, every deep drilling robot, every construction site for a future city requires more energy than entire nations consume on Earth today. This is the fundamental challenge that our eighth concept addresses, the creation of a space-based solar power grid. Imagine placing vast fields of solar panels not on the dusty surface of Mars, but in the pristine vacuum of space around it. In orbit, there is no atmosphere to filter the sunlight, no clouds to cast shadows, and no rotation of the planet to create a cycle of day and night. The sun shines with uninterrupted intensity 24 hours a day, 7 days a week. These orbital arrays would be colossal, stretching for hundreds of miles, their surfaces constantly angled to drink in the pure stellar energy. But generating the power is only half the solution. The true innovation lies in how we deliver it. This colossal energy would be converted into a tightly focused beam of microwaves or low-intensity lasers, a perfectly safe and invisible cord of power stretching from the sky to the ground. On the surface, vast receiving stations, which might look like enormous, open mesh fields, would catch this beam and convert it back into electricity, feeding a global power grid for the fledgling world. This is not just about turning on lights, it is about fueling the very heart of the terraforming effort. The atmospheric processes that breathe new gases into the sky, the drills that awaken ancient underground aquifers, the factories that produce synthetic greenhouse gases, all would draw their life from this celestial power source. It becomes the silent, indispensable backbone of the entire endeavor, a constant flow of energy that allows every other system to work in concert. Without this reliable and sustainable grid, the transformation of a planet would stall, a dream starved of the very power needed to make it real. This foundational energy source paves the way for the next great challenge, one that moves from global power to hyper-local precision, managing the very weather we would create. The barren ground beneath our feet holds the potential for life, but it must first be taught how to live. This is the challenge of regolith farming, a process that turns sterile dust into living soil. The powdery regolith covering worlds like Mars and the Moon is more than just dirt. It is a complex mineral substrate that lacks the organic matter and microbial life that makes Earth's soil so fertile. Our first step is to send in the smallest of pioneers, custom-engineered bacteria and fungi. These microscopic organisms are the planet's first farmers, tasked with the monumental job of breaking down the tough, rocky material. They will slowly digest the minerals, releasing essential nutrients like nitrogen, phosphorus, and potassium, and in doing so, they will begin to create the very first crumbs of a substance that could one day be called soil. This newly activated regolith is then mixed with organic matter, which in the early stages of a colony would come from a very familiar source, composted biological waste from human habitation. This combination of processed rock and recycled organics creates a crude but functional growth medium. The next wave of life would be hardy, genetically engineered plants, designed with deep root systems to further break up the ground and leaves that can be composted back into the soil after harvest. This creates a closed-loop cycle, a tiny, self-reinforcing ecosystem where nothing is wasted. Over decades, this careful cultivation, this patient act of feeding the ground, would transform the regolith into a rich, dark, and truly living soil, teeming with earthworms and beneficial microbes. This is not merely agriculture, it is the creation of a biosphere's foundation. A single handful of this new soil would represent a profound achievement, containing within it the entire history of the colony's effort and the future promise of a world that can feed itself. It is the bedrock upon which every other aspect of a living world will ultimately depend. The power to reshape a world must be tempered by profound foresight. Before we ever warm a single polar cap or release a single engineered microbe, we would need to simulate the entire process, not for years, but for millennia. This is the vital role of planetary climate modeling supercomputers. These would not be ordinary machines, but colossal digital oracles, likely harnessing the strange, parallel logic of quantum computing to map the infinite variables of an alien world's climate system. They would need to model the complex interplay of atmospheric chemistry, ocean currents, solar radiation, and geological activity, all while predicting how our interventions would ripple across centuries. The goal is to see the unintended consequences before they become irreversible realities. For instance, a model might reveal that a particular greenhouse gas mixture, while warming the planet effectively, could also trigger a chemical cascade that would eventually strip the atmosphere away entirely. Or it might show that melting the northern ice cap too quickly would create a localized deluge, reshaping the planet's geography in ways we never intended. This predictive power acts as our essential safeguard, a digital testing ground where we can fail without causing actual harm. It forces us to confront the long-term responsibility of our actions, ensuring that our desire to build a new Earth does not lead us to accidentally break one beyond repair. This careful, calculated approach stands in stark contrast to our next concept, which asks a far more radical question. What if the most profound changes are not made to the planet itself, but to the very beings who would call it home? A single, violent impact delivers water all at once, but a more patient and controlled approach would treat this vital resource as a continuous flow. This is the promise of Comet water delivery networks, a system that reimagines the outer solar system as a vast reservoir. The process begins far beyond the orbit of Neptune, in the deep freeze of the Kuiper belt or the distant Oort cloud. Here, robotic scouts would identify ideal candidates, small, pristine comets composed almost entirely of water ice, untouched relics from the solar system's birth. These cosmic icebergs would then be captured not with nets but with gentle, persistent force. Low-thrust ion engines or solar sails attached to the comet's surface would fire for years, gradually altering its trajectory. Instead of a collision course, these engines would guide the comet into a stable, distant orbit around the target world, like Mars. Once in place, the true harvesting could begin. Orbital facilities would process the comet, using focused sunlight to vaporize patches of its surface. This liberated water vapor would then be captured and condensed into liquid, ready for transport. But how do you move an ocean from orbit to the ground? One elegant solution involves the use of orbital elevators, tethers stretching from the surface to a point beyond geostationary orbit. These elevators could carry massive containers of water down to the surface with minimal energy cost. An even more futuristic method would employ directed energy beams, powerful but precise microwaves that would gently heat the falling water, transforming it into a controlled, steady rain that could be directed into waiting basins and newly formed river valleys. This system allows for the careful, deliberate construction of a planetary water cycle. We could start with a single inland sea, monitor its effect on the local climate, and then, only when ready, deliver more water to create a second. It is planetary plumbing on the grandest possible scale, giving us a dial to control the humidity, the rainfall, and the very formation of oceans. This method of slow, deliberate infusion stands in stark contrast to the planetary scale upheaval of our next concept, which asks if we should move entire worlds themselves to find the perfect home. A planet's rings are no longer just features of distant gas giants. They can become the ultimate climate control system, engineered by human hands. This concept envisions surrounding a world like Mars with a thin, artificial band, a necklace of countless intelligent particles, each one a tiny, autonomous spacecraft. Unlike the icy rings of Saturn, these would be precisely controlled, able to shift their density and angle to cast deliberate shadows across the planet's surface. Imagine being able to cool the scorching equator of a newly warmed world, creating more temperate zones ideal for settlement, while allowing the poles to remain bathed in sunlight to prevent a new ice age. This is planetary air conditioning on a scale that defies belief, a dynamic shield that actively manages solar exposure across entire continents. But these rings would serve a dual purpose. Many of the particles could be coated with ultra-efficient solar cells, turning the entire structure into a single, unbroken power station orbiting the planet. They would capture the pure, unfiltered energy of the sun and then transmit it not with clumsy cables but via focused energy beams down to receiving stations on the surface. This creates a permanent, resilient energy grid woven into the sky itself, one that could never be disrupted by a dust storm or a dark night. The psychological impact of such a structure would be profound. For every future generation born on that world, the rings would be a constant, majestic presence in the heavens, a visible reminder of the power and ambition that built their home. It stands as a bridge between the practical needs of a civilization and its highest aspirations, a declaration that our engineering can reshape not just the ground we walk on, but the very sky we look up to. Sometimes the grandest visions begin with the smallest sanctuaries. Rather than transforming an entire planet, we could start by building a single, perfect room. On an airless world like our moon, this approach becomes a practical and powerful first step. Deep within the polar craters, places where the sun never rises and temperatures hover near absolute zero, we find the perfect location for a new kind of home. These are not just holes in the ground, they are natural vaults, already shielded from solar radiation and the constant rain of micrometeorites. Their greatest treasure lies hidden in the eternal darkness, vast deposits of water ice preserved for billions of years. Our task would be to cap one of these colossal craters with a dome of transparent, multilayered material, strong enough to hold back the vacuum of space yet clear enough to let in the distant Earth light. Once sealed, this enormous cavity would be filled with a breathable, pressurized atmosphere, creating a self-contained world under a single roof. The interior of this crater city would be a carefully engineered paradise. Using the local water for both life support and to create a soil substrate, we could cultivate forests, farms, and freshwater lakes, all arranged in terraces along the ancient crater walls. The entire system would be a closed loop where every drop of water and every molecule of air is constantly recycled. This is not merely a base, it is a prototype, a miniature Earth in a bottle. It serves as the ultimate testbed for the technologies we would need for full-scale terraforming, allowing us to practice managing an entire biosphere in a controlled, observable environment before we risk altering a whole planet. The success of such a crater ecosphere would prove a profound and hopeful truth that we can carve out pockets of life and warmth in the most desolate and unforgiving corners of the cosmos. The air we breathe is mostly nitrogen, a silent, foundational gas we scarcely notice until it is gone. To build a truly stable and breathable atmosphere on a world like Mars, we would need to provide it with this essential buffer gas, creating the pressure necessary for liquid water and the background against which oxygen can be safely metabolized. Mars itself offers only trace amounts, a thin scattering of nitrogen atoms utterly insufficient for the task. The solution, however, does not lie in synthesizing it, but in a grand voyage of acquisition, reaching across the solar system to a place where nitrogen flows like a vast, unending river. Saturn's largest moon, Titan, is shrouded in a thick, hazy atmosphere composed almost entirely of this precious resource. It is a natural reservoir on a colossal scale, holding more accessible nitrogen than the entire Earth. An astroengineering project of breathtaking ambition would involve sending automated fleets to this distant moon. These would not be landers, but atmospheric skimmers, vessels designed to plunge into the upper layers of Titan's orange haze. As they glide through this alien sky, they would open massive intakes, swallowing tremendous volumes of the thin, cold air. Onboard processing plants, powered by compact nuclear reactors, would then work continuously, using advanced filtration and chemical separation to isolate the pure nitrogen, compressing it into frozen blocks or supercooled liquid for its long journey home. This is not a one-time mission, but the establishment of a permanent supply chain, a cosmic pipeline stretching over 1 billion miles. It redefines our relationship with the solar system. We would no longer see planets as isolated outposts, but as specialized nodes in a single, integrated economic and biological network. Titan becomes the quarry, Mars the construction site, and the space between them a highway for the raw materials of worlds. The successful operation of such a system would mark a fundamental shift in human civilization, proving our ability to manage resources not just on a planetary scale, but across the entire reach of our star's influence. Deep beneath the frozen crust of a distant moon, a world of liquid water and potential warmth awaits its awakening. On ocean worlds like Europa and Enceladus, the greatest source of energy is not beamed from the sun, but churns relentlessly from within, generated by the immense gravitational pull of their parent planets. This constant, rhythmic flexing creates friction deep in their cores, producing vast reservoirs of geothermal heat. Our task would be to tap into this inner furnace. We would deploy autonomous, deep-drilling cryobots, machines designed to melt their way down through miles of solid ice. These self-guided probes would descend into the eternal darkness, carrying with them a power cable and a communication link, a slender thread connecting the surface to the ocean far below. Upon breaking through, they would release their heat, not in an explosive flash, but as a steady, radiating warmth. This deliberate infusion of thermal energy would act as a catalyst, expanding existing pockets of water and melting surrounding ice to create vast, stable, liquid water cavities suspended within the ice shell. These would not be dark, empty voids. The same geothermal forces that heat the water also power hydrothermal vents on the ocean floor, systems that on Earth are thriving oases of life, independent of sunlight. Around our artificial warmth, we could cultivate similar ecosystems, introducing specially engineered microorganisms and simple aquatic plants that feed on the mineral-rich waters. These would form the foundation of a new, self-sustaining food web, all thriving in a protected, subglacial sea. The ice shell itself becomes a monumental advantage, a natural roof kilometers thick that shields this nascent biosphere from the lethal radiation bathing the moon's surface. This approach redefines the concept of a habitat. We are not building a dome on a barren plain, but rather kindling a fire in a ready-made subterranean cathedral. It suggests a future where life could flourish in the most unexpected places, not on the surface of worlds, but in the warm, dark hearts of their frozen satellites. The thick, soupy atmosphere of Venus is a chemical prison, but we hold the key to its transformation. This key is photolytic atmospheric conversion, a process of planetary-scale chemistry that uses pure, focused light as its scalpel. Imagine vast orbital platforms, their surfaces covered not with solar panels, but with immense parabolic mirrors or banks of high-efficiency lasers. These are not power generators, but molecular disassemblers. They gather the intense, unfiltered sunlight of the inner solar system and concentrate it into beams of incredible power, which are then aimed downward into the planet's oppressive cloud tops. Their target is the carbon dioxide molecule, the very brick from which Venus' atmospheric prison is built. When struck by this concentrated energy, the molecular bonds that have held the carbon and oxygen atoms together for eons are shattered. In a flash, what was a molecule of poison is split apart, leaving behind its elemental pieces, carbon monoxide, and most importantly, pure, breathable oxygen. This is photolysis, the same fundamental principle that allows a leaf to create oxygen from sunlight and air, but here amplified to a staggering, global magnitude. It is chemical surgery performed on a planetary patient, a deliberate and precise dismantling of a toxic environment, rebuilt one molecule at a time into the very air we need to live. The challenge, of course, is one of staggering scale. To make a meaningful dent in an atmosphere as massive as Venus, these converters would need to operate continuously for centuries, their silent beams working day and night to slowly bleed the planet of its carbon dioxide and seed its skies with life-giving oxygen. It is a testament to a quiet, persistent form of power, the power not of impact or force, but of patient, focused illumination. This act of creation through deconstruction forces us to confront an even more radical proposition. If we can rebuild the air itself, what other fundamental planetary properties are within our reach to alter? The color of a world is far more than mere appearance. It is a powerful statement of its climate. A bright, reflective surface bounces sunlight back into space, keeping the planet cool, while a dark, charcoal-gray landscape soaks up that same energy like a sponge, heating the ground beneath it. This fundamental property, known as a planet's albedo, becomes a lever we can pull to guide a world's temperature. On Mars, we could enact a planetary-scale makeover, one with two very different goals. To cool specific regions, we might dispatch fleets of autonomous rovers to blanket the vast, dark basalt plains with a fine, shimmering layer of silica dust or ultra-thin graphene sheets. This would be like giving the planet a mirror, turning areas that once absorbed heat into brilliant reflectors that cast solar energy away. Conversely, if we needed to accelerate the melting of the polar ice caps to release their trapped greenhouse gases, we would do the opposite. The same rovers could be directed to sprinkle those brilliant white caps with a carefully measured layer of dark, carbon-rich dust. Suddenly, the pristine ice would no longer reflect the sun's rays, but would instead begin to absorb them, warming from within and hastening its own transformation from solid to gas. This is geoengineering on a truly heroic scale, a patient and precise method of tuning a planet's global thermostat. The adjustments would be gradual, taking place over centuries, allowing the climate systems to respond without shock. It demonstrates a breathtaking level of control, the ability to not just build on a world, but to repaint its very surface in order to rewrite its future. After mastering the art of reflecting and absorbing light, our attention turns to the very ground we stand on, and the possibility of constructing an entirely new foundation for life. The transformation of a planet begins with a single, silent command. This command activates the seed of an industrial revolution unlike any other, a swarm of robots designed not just to work, but to create more of themselves. These are not individual machines, but a collective intelligence, a decentralized workforce capable of exponential growth. The initial payload sent from Earth would be modest, perhaps a single shipping container filled with the core components for a few hundred of these robotic pioneers. Upon landing, they would immediately disperse, their programming focused on a single, primal objective: to find and consume the raw materials of their new world. They would mine iron, silicon, and rare earth elements directly from the soil and rocks, feeding these materials into mobile, automated fabrication units that are part of the swarm itself. From these portable factories, new robots would emerge, identical to their creators, ready to join the effort. What starts as hundreds soon becomes thousands, then millions, and eventually billions, a tide of intelligent machinery washing across the globe. Their tasks are as varied as the transformation itself. Some would be earth movers, sculpting the land to create riverbeds and shorelines for future oceans. Others would be construction units, assembling the foundations for cities and the vast arrays of solar panels needed to power everything. A third type might be processors, dedicated to grinding the sterile regolith and treating it with chemicals to prepare it for the arrival of life. The true power of this system is its resilience and adaptability. If a dust storm buries a solar array, a subswarm is automatically dispatched to dig it out. If a new mineral vein is discovered, the nearest robots alter their programming to exploit it. There is no central command center to be destroyed, no single point of failure. The swarm is the system, a living, breathing, and growing entity of metal and silicon. This approach turns the greatest challenge of astroengineering, the sheer, back-breaking scale of the work, into its greatest asset. Human overseers would not micromanage every robot, but instead set broad, strategic goals for the swarm's collective intelligence to interpret and execute. We would become the architects of the vision, while the swarm becomes the countless hands that bring it into being. This mechanical genesis raises profound questions about autonomy and purpose, hinting at a future where the line between a tool and a partner becomes permanently blurred. The silent, exponential growth of a robotic swarm creates a voracious demand for raw materials, a need that rockets could never hope to satisfy. Each launch from a planetary surface is a violent, expensive, and fuel-intensive act, a bottleneck that would strangle any grand project of astroengineering before it truly began. We require a system that is the antithesis of a rocket's explosive departure, a method that is as calm and constant as the turning of a planet. The solution is a structure of almost mythic simplicity and ambition, a space elevator. Imagine a ribbon, a cable woven from carbon nanotubes, stretching from the surface of Mars or Earth out into space, reaching a point over 22,000 miles high where centrifugal force keeps it perpetually taut. This is not a tower built from the ground up, but a tether dropped down from the heavens. An anchor station on the planet's equator forms its route, while a massive counterweight, perhaps a captured asteroid or a purpose-built station, holds the far end steady in geosynchronous orbit. Along this celestial highway, robotic climbers would ascend and descend, powered not by volatile chemical explosions, but by beams of energy projected from the ground or from the station above. Their movement is a silent, steady crawl, a continuous procession of cargo that makes the journey to orbit as routine as a freight train crossing a continent. The economic and logistical transformation would be absolute. Suddenly, lifting the massive components for orbital mirrors, the prefabricated sections of a magnetic field generator, or even the water harvested from distant comets becomes a matter of scheduling and power management, not a heart-stopping, one-in-a-million launch. More profoundly, the elevator enables a two-way street. Vast quantities of raw materials mined from metal-rich asteroids could be brought down the cable with minimal energy cost, providing the literal building blocks for the new world below. This turns the entire concept of resource scarcity on its head, making the movement of planetary mass a routine industrial operation. The space elevator becomes the great enabler, the indispensable logistical spine that connects a planet's surface to the infinite resources of its orbital space, turning isolated celestial bodies into interconnected hubs of a solar system-wide civilization. This mastery over matter and gravity forces us to confront our final and most profound concept, one that asks not how we will build new worlds, but what we will become when we live within them. The final and perhaps most vital concept is not a technology, but a set of guiding principles. Our newfound power to reshape worlds must be matched by a profound and universal wisdom. This is the imperative for ethical frameworks and planetary protection protocols. Before a single mirror is deployed or a single microbe is released, humanity would need to engage in a global conversation, one that establishes international treaties and binding ethical guidelines for astroengineering. These are not mere suggestions, they are the essential guardrails for our cosmic ambition. They force us to confront difficult questions that have no easy answers. Do we possess the inherent right to alter the fundamental nature of another world, to overwrite billions of years of its unique geological history with our own vision? And what happens if, in our eagerness to build, we discover the faint, silent signature of native microbial life, a biology that represents a second, independent genesis of life in the universe? To proceed without answering these questions would be the height of arrogance, risking the irreversible loss of irreplaceable scientific knowledge and potential cosmic heritage. The protocols would ensure that our expansion is conducted with foresight and a deep-seated respect for the intrinsic value of other planetary bodies. This is not about halting progress, but about steering it with a steady hand and a clear conscience. It is a crucial conversation that must happen in parallel with the development of the technology itself, for the tools we build are only as wise as the hands that guide them. The ultimate success of our journey to the stars may not be measured by the worlds we build, but by the wisdom we demonstrate in caring for them. From orbital mirrors to self-replicating robots, these 20 astroengineering concepts sketch a future where humanity is no longer a passive resident of Earth, but an active force in the cosmos, learning to sculpt planets to our needs. This journey from imagining these ideas to actually realizing them will be the single greatest undertaking in human history. It will demand levels of international cooperation we have never achieved, technological innovation that pushes the very boundaries of our understanding, and an ethical framework that guides our immense new power. This is a challenge that forces us to think not in terms of years or even decades, but in millennia, planning for generations we will never meet. As we stand on the brink of becoming a multi-planetary species, the ability to shape entire worlds comes with a responsibility that is equally vast. The ultimate question may not be whether we can achieve these wonders, but whether we possess the collective wisdom to do so with care and foresight. Which of these concepts excites or concerns you the most? Share your thoughts in the comments below, and if you want to continue exploring the future with us, be sure to subscribe.